For this video, I will be looking at using Excel to analyze probabilities and how using conditional probabilities can assist when making predictions, and then I will discuss the use of different Bernoulli distributions. The dataset I will be using for this is found from Kaggle, a link will be in the description, and it is on statistics for every player for every game they played in the AFL from 2012 to 2024. There is also another sheet on player data, which I will also use for a part of the video. Before we start, I'll quickly explain how I clean the data. Here in the clean sheet, you'll see that I have only taken the data from 2024 out for this analysis, since the original dataset had 118,000 entries, to avoid excessive lag and to focus on the most recent year. I also filtered the column % played to only show entries greater than 50%, to exclude any players who played as the emergency sub most of the game or were injured early in the match. I also used Ctrl A and F5 to ensure there were no blank values. Now this doesn't mean the data is fully cleaned and perfect, but it definitely helps to narrow the dataset to the most relevant and reliable entries. Let's start by looking at the probabilities of kicking 2+ and 3+ goals, which I've labelled as Event A and Event B. To get the probability of 2+ goals, I just used the COUNTIF function to count how many rows have more than one goal, and then divided by the total number of entries. That gives about 13.7%. For 3+ goals, I used the same method but changed the condition to greater than 2, which gives about 5.1%. Now if I open Paint here, you can see how the Venn diagram works. Because every 3+ goal game is also a 2+ goal game, Event B is a subset of A, so the Venn diagram would look like it does on the right. So the union, A or B, is just the 2+ goal probability in green, and the intersection, A and B, is the 3+ goal probability in red. You can see these put in here. This 100% stacked column pivot chart also shows it clearly. The light blue section is 3+ goals, the green and light blue section combined are 2+ goals. So light blue is the intersection, and both together is the union. This also leads into conditional probability. Since B is a subset of A, the probability of 2+ given 3+ is just 1, because you can't kick 3 without kicking 2. The reverse, 3+ given 2+, is light blue divided by the total of green and light blue, or the intersection, which equals the probability of 3+ goals, divided by the probability of 2+ goals. That's around 37.2%. So basically, if a player kicks at least 2 goals, there's about a 37% chance they go on to kick 3 or more. Now let's make it a little more complex. I've filtered the data by team, looking at Sydney and Richmond since they finished first and last on the ladder in 2024. This changes a few formulas. Instead of average, I now use average if to only average games played by Sydney or Richmond. For counting, I've switched to COUNTIF for total games and COUNTIFs to count how many games had 2+ or 3+ goals and for each team. The union, intersection and conditional probability calculations are the same as before, just now filtered by team. Unsurprisingly, Richmond's averages and goal probabilities are much lower than the average, which makes sense. What's more interesting though is Sydney. Whilst I have a much higher probability of 2+ goals than average, and a marginally higher probability of 3+ goals, they have a probability of 3+ goals given 2+ goals that is actually lower than the average. That seems odd. Sydney finished first, but to add context from watching them, they spread their goal scoring more evenly across players. Adding teams to the pivot chart helps to prove this. Sydney has the smallest proportion of 0 goal entries, meaning they have the highest number of entries with 1 or more goals, shown by the dark blue area on the chart. They consistently score, but don't rely on just one big goal scorer. So this begs the question, is the probability of 3+ goals given 2+ goals effective at predicting ladder prediction? To test this, I manually added a ladder position column to this table below and plotted it against a few goal-related probabilities. 0 goals versus ladder rank had a moderate negative correlation with an R-squared value of 0.618. 2+ goals had a slightly weaker positive correlation with an R-squared value of 0.584, But 3 plus goals given 2 plus goals showed almost no correlation with an R-squared value of 0.012. So that conditional probability isn't a useful predictor for ladder position. But how useful is 0 goals as a predictor? We can use the formula of the predicted trend line on this graph, which is 134.83 multiplied by the probability of 0 goals, minus 78.844. When I tested this by adding a column to the table, the predictions were off by an average of around 2.7 spots, and only 2.4 spots when ranking the ladder by ordering the expected value. This allows it to be a possible predictor of ladder position for future seasons. We can simulate and test this using 2023 data, which I have done in this sheet. I'm not going to go in depth on this, but the differences remain similar except for Carlton, which is a large outlier, being 10 places off. This works to prove the trend line is not just a coincidence, and shows it has potential to be useful for predicting future ladder positions, given only the probability a random game from a random player of that team will have 0 goals. Now let's take this further by filtering based on traits. For this I am going to need height and position data for players, which is present in a different table. Luckily, both tables have the same player ID values, which allows me to use the VLOOKUP formula in a new column to get the information I need. First I looked at height over 195 centimeters. Let's say event A is kicking 2 plus goals, and event B is being taller than 195 centimeters. From that, we need to work out 2 things. The intersection, which is players who are tall and kicked 2 plus goals, and the union, which is players who are tall or kicked 2 plus goals, or both. Since A and B are now unrelated, B is no longer a subset of A when B was 3 plus goals. We need to use count ifs and filter for both goals being 2 or more and height being over 195 centimeters, and then dividing by the total, which is still 9,314, to find the intersection. For the union, we use the union intersection formula by adding the probabilities of A and B and subtracting the intersection, which we just found. Now that we have this, we can find the conditional probabilities both ways, but for the sake of simplicity, I'm going to focus on the probability of 2 plus goals given height, or A given B, which is the intersection divided by the probability of B. What's interesting is that the probability of 2 plus goals given the player is tall jumps to about 17.9% compared to the overall 13.7%, so taller players do tend to kick more goals. Then I filtered by position, just looking at forwards and doing the exact same process. That conditional probability jumped even higher. The probability of kicking 2 plus goals given the player is a forward was about 31.9%. So forwards are clearly more likely to kick multiple goals. To compare, I also did a random filter by picking players whose names start before D. That probability of 2 plus goals dropped below the average to 12.7%, which is reassuring because it suggests that you can't just pick any filter. Lastly, I tried combining traits, players who were both over 195 centimeters and forwards, with forwards becoming event C. A lot of these intersections and unions I just copied over from before, but the A intersection B intersection C is important, and is a count ifs function with all 3 filters. Now, by finding the probability of A given B intersection C, I'm finding the probability of 2 plus goals given a player is over 195 centimeters and the forward. You'd expect that to increase the probability even more, but it actually dropped to 24.7% compared to forwards alone at 31.9%. One reason for this is how players are categorized, since it is subjective. For example, I found a key forward with very few hitouts still labelled as a ruck, which would exclude them from a forward filter, despite consistently kicking goals. However, it could also suggest that whilst taller players are more likely to kick 2 plus goals, once you know it is a forward, that's not necessarily the case, especially since many tall players will play multiple positions over time, such as ruck and forward or key defender and forward, which can become inaccurate since they only get labelled with one position across a potential 13 years in the dataset. So, overall, in this dataset, while height gives some predictive value, the forward position is far more reliable, and combining both can actually hide some key tall goal-kicking players due to subjective labeling and removes any high goal-kicking small forwards. For the remaining portion of the video, we're going to focus on a hypothetical question. Let's say you're drafting entries from this list to make a team. This team would then play the game with the game stats present in the entry. But what if we want to have a certain number of players with a given stat? For this, we are going to choose disposals being greater than 30. This allows us to use a variety of probability distributions, given every entry selection has a Bernoulli distribution. Firstly, we need to find the number of entries with more than 30 disposals, which is easy. We just use the COUNTIF function for all disposals greater than 30 and divide by the total number, which is 9,314. This gives us a probability of about 3.6%. We'll start with a binomial, for which we need two parameters. We already have p, but what is our value of n? In this scenario, let's say we are picking 2 teams worth. By working out the average number of players in each game, by counting the unique game IDs, we can round to the nearest 2. So each team has an equal number of players, which gives us a value of n equals 42. We do this step since we have filtered out players with less than 50% time on ground. Now the rest is easy. Excel has formulas for the binomial distribution, and we can create 4 columns. The first with the value of x, the second with the binomial distribution non-cumulative, and the third one with the binomial distribution cumulative. This third column shows the probability that x many or fewer greater than 30 disposal players are drafted. The fourth column is simply 1 minus the third column to show the probability that x many or more greater than 30 disposal players are drafted. We can see, given the small probability, it very quickly becomes highly unlikely to see even at least 4 players, at around 1.7%. Also, the expected value, which is n times p, is only about 1.5 greater than 30 disposal players, which fits with the graph of p of x is x, showing that the most likely values of x are 1, then 2, and then 0, before a sharp decline. We can also make a Poisson approximation of this value, using n times p as our value for lambda. Here we can see that the approximations are quite close, especially for smaller values of x, but since n is 42 and p is 0.036, the value of n is likely not large enough, and the value of p is likely not small enough for the approximation to be too accurate. Earlier, I mentioned that there was only 1.7% chance of seeing at least 4 greater than 30 disposal players. So, how many draft options will be needed to require 4 greater than 30 disposals to become more likely than, say, above 50%? This is where we use a negative binomial distribution, where x counts the number of fails upon the 4th success. I chose to do cumulative only for this, since probabilities of any exact x would be extremely low. It takes 98 fails, or a total of 102 drafts, with the 4 successes for there to be greater than a 50% chance of 4 greater than 30 disposal players existing. However, if we increase the value to 122 fails, or 126 drafts with the 4 successes, it becomes about a 66.8% chance, or a little over 2/3 chance, of 4 greater than 30 disposal players. Since 126 is 42 times 3, each draftee can select from between 3 players for each turn as a suitable solution to the problem. And this value now exceeds the expected value of 107 fails, or 111 drafts. In summary, this video used AFL data from 2024 to analyze goals and disposals and express how to find probabilities, model the effectiveness of probabilities at predicting outcomes, and using probability distributions to find the probability of selecting a certain number of players with a given statistic.